Okay, let me share my screen. Can you see my screen?
Yeah. Yes. Yes,
Okay,
sir.
fine. Uh, just a minute. So this orientation is better or this orientation is better? First one or this one? Hello?
This
This
one.
one better, sir.
This one is better, right? Okay, this one is better. So today we will start with modeling of a three-phase wound rotor or slip ring induction motor in any arbitrary rotating DQ reference frame. As I said, arbitrary means a DQ reference frame, a reference frame that is rotating with the with some arbitrary angle. So, which is rotating with some arbitrary angle or with some arbitrary speed omega. Omega is the rotating speed and theta is the angle of the instantaneous angle of that DQ reference frame. Okay, so that reference frame, arbitrary DQ reference frame is defined as any reference frame rotating at an angle of omega and whose instantaneous position is given by theta, which is means basically integration of it, integration of omega t plus theta naught, where theta naught, let's assume that the initial angle is 0 degree. So as I have also mentioned in the last lecture, that the stator of a induction motor is nothing but it has distributed windings. Distributed means the stator construction includes parallel slots, and inside that slots we keep bundles or bunches of conductors in each of the slots, and then we electrically connect all these conductors in such a way that on the panel of the induction machine we have six terminals. That six terminals we can connect in a star connection or in a delta connection. There are different benefits of using star and delta connections. If you want more starting torque, or if you want less current or more current, so based on that you can connect the motor. So as we are exciting the motor, what happens is these stator conductors get this power supply, and as the conductors are placed in these distributed slots, and as the electrical supply is of sinusoidal nature, which is V sine of omega t for A phase, for B phase V sine omega t minus 2 pi by 3, for C phase V sine omega t plus 2 pi by 3. So as the electrical quantities, all the three quantities are sinusoidal in nature, and as the conductors are placed distributed in nature in a circle, so the resultant flux produced by the current flowing into the stator coils will be of rotating nature. So that flux vector will be of rotating nature. So using the assumption of using the primitive analysis of motor modeling, what we can do is, as I have told earlier, that we are analyzing this machine in three phase because we have a three phase supply. So if you can see in this vector diagram, what I have depicted is that there I have drawn three vectors. Here you can see VAS, this is the VAS, this is VBS, and this is VCS. So using the primitive motor concept, the induction motor can be assumed as a motor with with concentrated winding confined only on these axes, A axis, B axis, or C axis. So you can assume that the distributed winding is a concentrated winding whose flux is confined to these three vectors AS, BS, and CS. This is for only stator. In a rotor of induction motor, the rotor is also has distributed conductors where the conductors are short circuited. Similarly, we can draw three vectors. Here you can see stator is in yellow color and rotor will show in the light blue color. So AR, BR, and CR. As you know that the electrical quantities of stator are leading with respect to rotor because it is being excited. And because of this stator excitation, because of the interaction between the stator and the rotor magnetic fields, there will be some electromagnetic torque produced. So stator is the cause, and due to the stator flux, there will be rotor EMF induced, which has the electrical frequency of slip frequency. The electrical speed is of slip frequency. That's why the rotor quantities are a little bit lagging with respect to stator quantities. And as you know, we have already discussed in the space weather analysis concept that if you observe this vector diagram, AR seems to be leading with respect to AS. But actually, in electrical quantities, AR is lagging with respect to AS. So if AS is V sin omega t, sorry, Vs sin omega t, AR will be VR because it's a rotor quantity. So rotor induced, the peak value of rotor induced voltage is nothing but VR sine of omega t minus some angle, delay angle. And that angle is this angle, theta r, sine of theta r, where theta r is omega r into t. If theta is omega t, what is theta r? Theta r is omega r into t. Omega r of t. Omega r is the rotor speed, rotor's rotating speed. But what speed? Electrical speed or mechanical speed? This is the electrical speed, electrical quantity, because we are writing the signals in electrical system. This is the electrical counterpart of the rotor frequency, rotating speed, omega r, which is nothing but theta. Theta r is omega r into t. So the angle by which the stator quantities, voltage to voltage, current to current, or flux to flux, the rotor quantities are time delayed with respect to the stator quantities by some angle theta r, which is nothing but the instantaneous rotor position. Okay. So using the same primitive motor concept, the rotor windings can also be considered as concentrated winding, which are confined to these three axes. What are the axes? AR, BR, and CR. Correct? So what we did is we assume that the stator and rotor windings from distributed to concentrated. Why? Because as you know that if the resultant of like if you draw three-phase quantities, if you draw the vector representation of three-phase quantities, it can be depicted as a rotating phasor. So that's why, yeah, and the reason for the rotation of that vector is nothing but two things. First is the mechanical spacing between the conductors, which is 120 degree, and also the electrical phase difference between A phase, B phase, and C phase quantities. That's why you can assume distributed winding to be concentrated only across these three directions. So stator with respect to stator ABC axis, and rotor quantities or rotor conductors with respect to these rotor axis, which is nothing but AR, BR, and CR. Okay. Now you want to now as we discussed in the previous lectures, this these are the dynamic equations of the induction motor in ABC domain. So VS, VBS, VCS, VR, VBR, VCR. Instead of writing individual equation, I have written it in form of a matrix representation. So this is, so basically a 6 cross 1 vector. This is a 6 cross 6 matrix. Again 6 cross 1 vector. Again 6 cross 1 vector. So this whole big matrix is called as the capital R matrix, which can be represented as sub matrices RSS, RSR, RRS, and RRR. RSS has means, and each of them are 3 cross 3. 3 cross 3. So here you can see this is RSS. This is RRR, this matrix, this 3 cross 3 matrix. Sorry, RSR. This is R of RS, and this one is RRR. So you can see that RSR and RRS are nothing but zero matrices. Why? Because resistance doesn't include the mutual coupling term. Only the inductance will have the mutual coupling term. Okay. So that's why RSR and RRS will be zero, and RSS and RRR will be. So as you can see here, they are diagonal matrices. Here you can see only the diagonal terms are non-zero. Correct? Rest non-diagonal terms are all zero in RSS and RRR submatrices. So V whole big vector. So this vector can also be further split into two parts. This is 3 cross 1, this is another 3 cross 1. 3 cross 1 is for only stator quantities VAS, VBS, VCS. So these voltages are nothing but the supply voltages. For time being, we are assuming that we are exciting the rotor as well because it's a slip ring induction motor. So that's why VAR, VBR, VCR we have written. If it is a squirrel cage induction motor, then this sub matrix will be 0, 0, 0, 0. Okay. So V whole big vector equals to this whole big resistance vector, matrix R into the current vector IAS, IBS, this one IAS, IBS, ICS, IAR, IBR, ICR plus differentiation of flux linkages plus derivative lambda S, lambda BS, CS, lambda AR, lambda BR, and lambda CR using the Faraday's electromagnetic law. Voltage is nothing but the resistance drop, which is nothing but R into I plus differentiation of flux linkage. This is the basic principle of basically this is a KVL equation, Kirchhoff's voltage law equation. Similarly, the fluxes can be represented in terms of current using some linear relationship. Okay, so lambda. So this is a big 6 cross 1 matrix. Sorry. 6 cross 1 matrix. This is 6 cross 6. This is 6 cross 1. Again, this whole big matrix is called as the inductance matrix, capital L. Again, this inductance matrix has sub matrices LSS, LSR, LRS, and LRR. And in last lecture, we have seen how to derive these matrices LRS, LSR, SS, and SR. Sorry, SS and RR by using the dot product principle by just taking the projection of ABC quantities on DQ or basically DQ quantities on ABC quantities. So these inductance, so these are a function of theta. The inductance term matrices are nothing but function of theta. So these inductance matrices can be written as, so here you can see LSS and LRR look very similar. The only difference is these terms. This is LSS, this is LRR. LSS is the inductance term that is confined to the stator winding produced due to the current flowing through another stator winding. Oh, sorry. Sorry. LSS is the term in LS. Sorry. This LSS and this LSS is different. Okay. Sorry for the same representation. This. So basically, let us use some other notation. Let me write alpha SS. So here this is alpha SS, alpha SR, alpha RS, and alpha RR. These are the inductance matrix, capital alpha matrix, where alpha SS is this, alpha RR is this, alpha SR is this, and alpha RS is this. Okay. So in this alpha SS matrix includes the term, only the inductance term, which are confined only to stator terms. So there is no role of rotor in lambda SS matrix. So inside the lambda SS matrix, these term, so there are two types of term, LSS and LMS. Correct? There are two types of term in lambda SS matrix. LSS is the term, means basically LSS is the term that is the inductance for a winding due to the current in its own winding. So there is no mutual term here. So the first term is AA, second term is BB, third term is CC. What is the meaning of AA, BB, CC is that AA means this LSS term is nothing but the inductance in the A side valley coil due to the current flowing in the same A side valley coil. Means basically this is the A side valley coil. This one. This is the coil. Why coil? Because I told you a distributed winding is now assumed as a concentrated winding. So LSS is nothing but the inductance induced by the current flowing in a coil due to its own current. And LMS is nothing but the inductance induced in one type of stator winding due to the current flowing In other stator windings, how many stator windings are there? Three, right? AS, BS, one at AS, one at BS, and one at CS. So LMS is nothing but the inductance. Let's say if you want to find between AS and BS, BS is here, between AS and BS. So that term, inductance term, this is the inductance induced at the winding kept at AS due to the current flowing through the winding in the BS. This is the IBS. This is the IS. This is nothing but ICS. So basically, LMS is defined as the mutual term, but mutual between stator and stator only. This is not the mutual term between stator and rotor. That we will see only in lambda SR and lambda RS matrix. So similarly, lambda RR is also has two terms, LRR and LMR. LRR is nothing but the inductance in a rotor winding due to current in its own winding, and LMR is nothing but the inductance in any stator winding or stator coil due to the current flowing through other rotor windings. So rotor to rotor mutual. This is the rotor to rotor mutual. This is rotor to rotor self inductance, you can say. So as you can see that in a distributed winding, LSS, LMS, LRR, and LMR all are constants. So these whole submatrices are constant. LSS and lambda SS and lambda RR. These are all constant matrices. Now comes the problematic term that is called as the lambda SR matrix and lambda RS matrix. Lambda RS is nothing but a transpose of lambda SR matrix. So it has two types of terms. One is nothing but the MSR, one is nothing but theta R. MSR is constant, theta R is varying with time. As the rotor rotates, the angular position of the rotor changes. So theta R is function of time. Or basically you can say that this term is a function of rotor position. That is nothing but f of theta R. So in order to model the induction motor, you should accurately track the rotor position to get this inductance matrix so that you can substitute these sub matrices here and you can get a dynamic equation in terms of this equation if you substitute here. You know that you can't accurately track the means you can track, but what is our aim? Why do we model a induction motor in a DQ frame? Is that to get rid of this time varying terms cos theta r, cos theta r plus 2 pi by 3, and cos theta r minus 2 pi by 3. The other term is MSR term. MSR means the mutual coupling term between stator and rotor, not between stator to stator mutual, not the not the rotor to rotor mutual. MSR defines the mutual coupling inductance between a stator and some rotor winding, means stator to rotor mutual. So you have to get rid of this theta term. Okay. So as you know that in the last lecture, so these matrices, instead of writing a whole big 6 cross 1 matrix, we instead of writing this matrix, we can write this in terms of this. This you can see this equation. What is this equation? A big matrix which is nothing but 6 cross 1, 6 cross 6, 6 cross 1, 6 cross 1. Okay. So V vector ABCS, instead of writing the vector, I'll represent it by VABCS equals to RS into IABCS plus d by dt of lambda ABCS. Similarly for rotor, VABCR equals to RR into IABCR plus d by dt of lambda ABCR. Similarly for flux vectors, for the stator flux linkage vector, you can write lambda ABCS equals to LSS into IABCS plus LSR into IABCR. Why? See, have a look here. These three terms refer to lambda ABCS and the bottom three terms refer to lambda ABCR. Similarly, in this matrix, the top three voltage terms refer to VABCS and the bottom three terms refer to VABCR. That's why they are 3 cross 3. I think I made a mistake here. These are not 6 cross 1. These are 3 cross 1 terms. So this is a 3 cross 1 matrix. Only RS matrix. This is not R matrix, this is the RS matrix. So this is 3 cross 3. So this has to be 3 cross 1. This is 3 cross 1. Similarly, this is 3 cross 1, 3 cross 3, 3 cross 1, and 3 cross 1. Similarly, these are 3 cross 1, 3 cross 1, 3 cross 3. All the L terms are 3 cross 3, and all the currents are 3 cross 1. Similarly, we can write the rotor flux linkage equation as lambda IBCR equals to LRS into IABCS plus LRR matrix into IABCR. You know that you want to get rid of this theta term, so you want to model this equation in some other reference frame which is also rotating with some angle, some arbitrary angle. Okay, I mean, it may not be necessary that the DQ frame should rotate at theta r angle only. So as I told in the last lecture, the speed of rotation of a DQ reference frame can be, so it can be equals to the supply frequency speed, that is omega. Omega is 2 pi into Fs. So if Fs is the supply frequency of any stator excitation term, and if theta equals to theta s, it means that you are modeling the equation in the synchronously rotating DQ0 reference frame. That is called as synchronous DQ reference frame. So in case where theta equals to theta r, in that case it is called as the rotor rotating DQ0 reference frame, in where theta equals to theta r. So here, as I told you, this theta. Okay, let us first define the DQ reference frame. Let me use a red marker. So as I said, we want to model the equation in a common DQ reference frame. This is D, this is Q. What is the angle of the DQ reference frame with respect to A axis vector? It is theta. You can see this is theta. So theta can be anything. Theta can be theta s. So basically integration of 2 pi fs plus theta naught into t. Okay, or it can be theta r, or it can be 0 also. So that's why I'm calling this DQ reference frame as arbitrary rotating reference frame, because the speed of rotation of this DQ reference frame is not defined. It can be 0, it can be theta r, it can be theta s. Theta s means frequency of theta s means as per the frequency of the supply of the supply. What is the supply? It is the voltages v sin omega t. So that omega is omega s. So that's why if you integrate that omega s, you will get theta s. So if theta is theta s, it is called as synchronously rotating DQ reference frame. If theta is theta r, it is called as rotor so basically it is called as the rotating DQ reference frame. And if theta is 0, it is called as stationary DQ reference frame. If theta is 0, then that DQ reference frame is also called as alpha beta reference frame. And if theta equals to theta r, that rotor rotating reference frame is also called as, so the transformation from ABC to that DQ and that DQ to ABC is called as the Parkes transformation, where theta equals to theta r. And if theta equals to 0, DQ reference frame is also called as alpha beta reference frame. And the transformation matrix from ABC to this DQ and this DQ to ABC is called as Clark's transformation. Okay. The transformation matrices which we saw in the last lecture, those are called as Clark's or Parkes transformation. So here in this case, let's assume that you don't know the angle of the rotation of the DQ reference frame. So let's keep it as theta, but theta is arbitrary. Okay, it's an incomplete thing. So assume that the angle is theta. So you have to refer all these equations given here in a common DQ reference frame, which is rotating by the angle of omega. This is the omega. Okay, it is rotating at an angle of omega. Its angular position is given as theta. So what we did in the last lecture, we saw how to transform a ABC quantity to DQ using matrix transformation. How we did? We did by taking the projection. So what you do? You project A axis on D axis, AS axis on D axis, AR axis on D axis, BS and BR on D and Q axis, and CS and CR on D and Q axis. Also, you might have known very well that this DQ reference frame, there are two ways to represent the DQ reference frame. One is the angle with which it is rotating, which I already told you. It's an arbitrary rotating reference frame. You don't know the angle. Let's assume that it is theta. Other thing is the orientation. Orientation means D is leading Q, Q is leading the The angle of the reference frame is measured from AS axis to D axis or AS axis to Q axis. So that is called as convention. And we have already seen the four conventions in the last lecture. So arbitrary DQ reference frame means the angle of rotation of that reference frame is some arbitrary angle theta with some given arbitrary convention. Okay. We have yet not fixed the convention, but we know what is the transformation matrix for different conventions. This is called as generic matrix transformation. This is called as CDQ0 matrix. CDQ0 matrix is used if you want to convert any ABC quantities into a DQ quantity, and similarly this is called as CABC. This is used when you want to convert any DQ0 quantity in the ABC reference frame. So basically CABC is inverse of CDQ0, and also it is transpose of CDQ0. This we have already seen in the last lecture. So now we'll do the transformation. Very quickly we'll do the transformation. As you know, okay, so okay, you know that x dq0 is equals to c dq0 into x into ABC. Okay, what you did, you transformed the ABC quantity into a dq0 quantity. That quantity x can be voltage, current, or flux linkage, any quantity. Okay, so x dq0, which is nothing but 3 cross 1. This is 3 cross 3. This is 3 cross 1. X dq0 equals to c dq0 into x ABC. So what is x ABC? C dq0 inverse of x dq0. Correct? So substitute this thing in the above equation, the above four equations. These are the four equations. The equations highlighted in the blue. You have to substitute this thing in these equations. If you do that, and if you solve that equation, okay, so let's say, okay, let me do one thing. Let me just do, okay, so we'll take the first equation. The first equation is this one. VABC is RS into IABCS plus divided of lambda IBCS. Okay, what you do? See here. VABC became CDQ0 inverse VDQ0. Now, as the ABC axis of the stator and rotor are different, so that's why the transformation matrices for transforming any ABC quantity to DQ and DQ quantity to ABC, the transformation matrices will also be different. So the transformation quantity here is nothing but a generic quantity, CDQ0 and CABC. But if you want to transform ABC stator quantities to DQ, then you should use a matrix which is called as CDQ0S. Similarly, if you want to transform any rotor quantity to the same DQ reference frame, then you should use some different matrix CDQ0R. Why? Because the ABC axis of the stator and ABC axis of the rotor are not same in this case. So as you have seen here, so this CDQ0 is nothing but a function of this angle, theta plus phi. Okay, and phi depends on the convention. Means basically phi is known. Phi is 0 if convention is 1, phi is pi by 2 if convention is 2. So basically you know the phi. The only term here is nothing but the angle. So basically CDQ0 is a function of theta. The theta is the angle between the ABC and the required DQ reference frame. So for the stator quantities, what is the angle? What is the angle between AS and D axis or AS and Q axis? It is theta. And what is the angle between AR and D axis or AR and Q axis? What is the angle? What is the angle between this and this? Let me show you. Angle between AR and DQ. It is nothing but theta minus theta R. This angle. Correct? Sorry. This angle. This is what? Theta minus theta R. Correct? So the value of so CDQ0S will be a function of theta and CDQ0R will be a function of theta minus theta R. Okay. If we substitute this, what will happen is we were here. So C dq0 s inverse of v dq0 s is RS was already there in this first equation, RS into IABCS. What is IABCS? C dq0s inverse of I dq0s plus dy dt of differentiation of what? Lambda dq0s. Sorry, lambda ABCS. What is lambda ABCS? By using the above equation, C dq0s inverse of lambda dq0s. Okay. Now, if you multiply this equation on both LHS and RHS using the term C dq0s, so what happens is C dq0s inverse multiplied by C dq0s will be identity matrix. So that will be 1. Okay. Then you will get this equation which is mentioned in highlighted in the yellow. This is what you will get. The equation is dq0s equals to C dq0s into R into C dq0s inverse multiplied by I dq0s plus C dq0s into C dq0s inverse. What is the value of this? That is I. So what you can write here is you can directly eliminate this term and write plus. So you observe here that there is a some extra term observed here. That term is nothing but this term. The term is, so basically here it was d by dt of C dq0s inverse into lambda dq0s. It is differentiation of two terms, basically two matrices which are multiplied. So if you use the the product chain rule of differentiation, so what will it be? C dq0s inverse into d by dt of lambda dq0s, okay, plus lambda dq0s into d by dt of C dq0s, okay. So that's why you get two terms. And also you're multiplying on LHS and RHS with the term CDQ0S. So that's why CDQ0S into CDQ0S inverse will be I. That will be 1. So you'll get two terms. First term is this one, d by dt of lambda dq0s, plus second term is this one. That is CDQ0S into d by dt of CDQ0S inverse into lambda dq0s. Let us assume that this is some matrix called as E matrix. So basically, and also let's assume that this matrix C dq0s into Rs into C dq0s inverse of I dq0s. This is some matrix Rs in terms of dq. Let us use the nomenclature Rs dq. Okay. Let us assume that this is Rs dq. Okay. Now you have to find the values of these matrices Rs dq and E matrix. Let us write here ES because it is for stator. So similarly, if you write the equations for the other voltage terms in terms of, I will write here instead of, because it will be very confusing. Okay. So what you got is V in dq0s will be some matrix Rs dq into I dq0s plus d by dt of lambda dq0s plus some matrix of Es in dq multiplied by what? What was that matrix? Into lambda dq0s. Okay, okay, okay. Into lambda dq0s. Similarly, v dq0r. All of them are 3 cross 1. This is 3 cross 3, 3 cross 1, 3 cross 1. This is 3 cross 3 and 3 cross 1. V dq0r, which is 3 cross 1, equals to r dq, which is 3 cross 3, into I dq0r, which is nothing but 3 cross 1, plus d by dt of lambda dq0r, which is 3 cross 1, plus e r dq, some new matrix, which is 3 cross 3 into lambda dq0r, which is 3 cross 1. This is first equation. This is second equation. Now you want to find the values of this r dq, rs dq, then es dq and er dq. You want to find the values of it. Okay. Similarly for lambda dq0s. What is the term that you will observe? If we substitute here in these equations, where are the equations? These equations, lambda IBCS. If we just write, so basically for the lambda, so it will be this. I will write like this. Directly I will write. Is sum LSS in dq into I dq0s plus some new matrix. This is 3 cross 3, 3 cross 1, 3 cross 1. You have to find this. You have to find this. Sorry. LSR in dq, which is nothing but again 3 cross 3 into I dq0 r 3 cross 1. And the last equation is lambda dq0 r, which is nothing but 3 cross 1 equals to L SR in dq, sorry, LRS in dq, which is 3 cross 3. This you have to find, this you have to find, this you have to find, into I dq0 S 3 cross 1 plus LRR in dq, which is nothing but 3 cross 1 into I dq0 R, which is nothing but 3 cross 1. These are the new matrices which you got. So you have to find this matrix, this matrix, this matrix, this matrix, this, 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 and this. I'll just quickly write what is the value of this. So RS in dq, which is a 3 cross 3. Its value is given as C dq0s into RS, which was the original RS, right? Which we use for ABC, into C dq0s inverse. Okay. These were the matrices which we have found out. Similarly, RR in dq 3 cross 3. This is nothing but C dq0r into, this is 3 cross 3, this is 3 cross 3, this is also 3 cross 3. 3 cross 3, 3 cross 3, RR, 3 cross 3, and C dq0r inverse. This is nothing but 3 cross 3. So you have to find the values of this. You have to do multiplication. You have to multiply 3 matrices. Here also you have to multiply 3 matrices. Similarly, what is the value of ESDQ? Which is nothing but 3 cross 3. That you will find as here. Where it was? It was somewhere here. C dq0s into d by dt of C dq0s inverse. Okay. C dq0s multiplied by d by dt of C dq0s inverse. This is 3 cross 3. This is also 3 cross 3. What is the value of ER dq? It is nothing but 3 cross 3. It is C dq0r, which is nothing but 3 cross 3 multiplied by d by dt of C dq0r inverse. This is nothing but 3 cross 3. Okay, so we have written this 4 term, and last we have to write the values of the last 4 matrices, which is nothing but LSS dq 3 cross 3. What is the value of LSS dq? This is nothing but C dq0s into the original LSS matrix, which is nothing but 3 cross 3, 3 cross 3 into C dq0s inverse. Similarly, LSS, sorry, not LSS, LSR, LSR in dq. I'm going very fast because it is very manual work, and I just tell you how to use Python to find the values of these matrices. So just very quickly, I'll write this C dq0. So it is LSR. So this is C dq0s, which is nothing but 3 cross 3 into the original matrix LSR, which was 3 cross 3 into C dq0r inverse. You observe the pattern. For LSS, it was C dq0s into original LSS into C dq0s inverse. So let me first write, then we'll see the similarity. L R S dq, which is nothing but 3 cross 3. What is it? C dq 0 R 3 cross 3 into LRS. LRS 3 cross 3 into, these are all multiplied, okay? C dq 0 S inverse. And last matrix which we need to find is LRR dq, which is nothing but 3 cross 3, is given as C dq 0 R, which was 3 cross 3, into LRR, the original LRR, which was 3 cross 3 in ABC, LRR was in ABC, into C dq0R inverse 3 cross 3, 3 cross 3, 3 cross 3, and this was also 3 cross 3. Observe the pattern. So you have to solve all of this. You have to solve all of this to get the state space representation in terms of dq. Okay, so it is very manual work. So these values of these matrices, so where C dq0s is a function of theta, and also C dq0s inverse is also a function of theta. C dq0r is a function of theta minus theta r. C dq0r inverse is a function of theta minus theta r. Why I have written like this? I'll tell you. This was the original CDQ0 matrix, right? This one. So just in place of theta, put theta minus theta r for the CDQ0R. For CDQ0S, theta is theta. So that's why I use this matrix as it is used for CDQ0S. Okay. So this is called as the manual work. So much manual work you have to do. You have to solve 1, 2, 3, 4, 5. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have to solve 10. Sorry, not 10. 8 only. Ignore this two. You have to solve these many matrix multiplication. So it's not just multiplication. In this case, you have to find the differentiation of this matrix, d by dt of this thing. So one more thing. Here you observe that C matrix is a function of theta, and you are differentiating that with respect to time. So using the chain rule of differentiation, d by dt of C dq0s can be written as d by d theta. So C, let me just clearly write. C dq0s, which is a function of theta, right? You have to, and it is a matrix 3 cross 3. You are differentiating a matrix with respect to time, but it is a function of theta, not time. So you can write d by dou theta of what? C dq0s, which is a function of theta, and it is a matrix, so 3 cross 3, multiplied by what? Into d theta by dt, right? And what is d theta by dt? It is omega, which can be written as omega into dou theta of C dq0s, which is a function of theta. 3 cross 3. 3 cross 3. Correct? Similarly, for C dq0r, what you write? D by dt of C dq0r, which is a function of theta minus theta r. What you can write? Omega minus omega r into dou theta of C dq0r, which is a function of theta minus theta r, and it's a 3 cross 3 matrix. Okay, so you have to do so much of hard work to just get 4 equations. These 4 equations. These 4 equations. So I will show you a Python code for doing this transformation. Okay. Okay. So what we'll be using is, so basically what you observe that all the matrices were a function of some parameters. So here you can see C dq0s, C dq0r are function of some parameters like sigma, kd, kq, l, lss, lms, LMR, LRR. So basically, these are different. So these are matrices in terms of not constant numbers, but in terms of some constants. Okay. So we'll use the symbolic math tool in the Python. So what a symbolic math means, that symbolic math library is nothing but basically you have to write equation and you have to solve the equation. Let's say the equation is x square minus 3x plus 5 equals to 0. So it is a polynomial of order 2 in terms of known parameters. So what are the coefficients? 1, minus 5 and 2. But if you want to find the roots of ax square plus bx plus c equals to 0 in terms of the variables or in terms of the constant a, b and c, then MATLAB or Python can solve that for you, but you have to specify what is a, b and c. So for that case, you have to use symbolic math package of MATLAB or Python to define first what is A, what is B, what is C. Okay. So here also we are using the symbolic math library of Python. So I have used the Google Collaboratory platform, which is nothing but, so this is the Python code. Here I have initialized it. Oh, it is connected. So I hope you can see my screen. So very first line, here I have written import numpy as MP. Numpy because we are doing some linear mathematical uh, what you can say operations on the equation like multiplication, inverse, differentiation. So that's why numpy library is used for it. So importing all the required libraries like matrix, symbol, matrix, and simplify expression, then matrix, then symbolic. From symbolic pi library, you import the all the symbols. Then, as I told you, you have to mention some symbols. So here I have written LLS, LLR, LMS, LMR, MSR, RS, RR, T because time, omega, omega S, omega R, theta, theta S, theta R. I have mentioned that all are some symbols. Okay, all are symbols, and those are real values. So real equals to true. True. Okay, the real equals to true. Then I have mentioned the functions. Symbolic functions means function in terms of the previously mentioned symbols, but also function of time. So VS, VBS, VCS, VR, BR, VCR, IS, IBS, ICS, IR, IBR, ICR, lambda AS, lambda BS, lambda CS, lambda AR, BR, CR, VDS, VQS, V0S, VDR, VQR, V0R, IDS, IQS, I0S, IDR, IQR, I0R, and the last are flux. Lambda DS, lambda QS, lambda 0S, lambda DR, lambda QR, and lambda 0R. All these functions are real functions, function of time. So this is nothing but declaration. Theta is omega into t, theta s is omega s into t, and theta r is omega r into t. Okay. First step is you mention all the matrices in ABC. So find the equation in ABC. So what is LSS in ABC? It is a matrix of LSS, LLS plus LMS. So here you can see the output. So it's a 3 cross 3 matrix in terms of these symbols. What is the LRR matrix? This is the LRR matrix. Okay. What is the LSR matrix? I have mentioned here in terms of MSR and cos theta. So basically here you can see that it's written minus MSR into sine omega RT. So basically it's equivalent to MSR into cos of omega R into T minus 2 pi by 3. It has just written it in terms of sine. So that is not a problem for us. Basically here, because here I have written, see here you can see sim dot cos theta r, comma sim dot cos theta r plus 2 pi. Okay. Huh. I can't zoom here because it will edit it, and I don't want to disturb this code. Similarly, LRS in ABC is LSR in ABC, transpose of that. So it calculated the transpose. Now, as I told you, the DQ reference frame is arbitrary reference frame. So here I am mentioning the convention and the values of the constants KD, KQ, and K0. And as the convention is 1, psi is 0, sigma is 1. So if and if else statement I have written, and I have written the transformation matrix CS and CR. What is CS? CS is nothing but C dq0s. What is CR? CR is nothing but C dq0r, which I have already mentioned. And K1, K2, K3, 2 by 3 KD, 2 by 3 KQ, and 1 by 3 K0. And what is, so I have written two more matrices, CS inverse and CR inverse. What is CS inverse? It is C dq0s inverse. CR inverse is C dq0r inverse. Okay. Then first write the matrices R and N matrices in the ABC reference frame. So as I told you, RS in ABC is nothing but RS00, 0RS0 and 00RS. RR in ABC is nothing but RR00, 0RR0 and 00RR. Okay. Then comes the modeling. Now comes the modeling. Now comes identifying these matrices, these matrices, 8 matrices. First is RSDQ. What is the value of RSDQ? C dq0s into RS into C dq0s inverse. Sorry. So here it is. RS in DQ is what? CS into RSABC into CS inverse. And I have written and simplify. So basically, any term that has the decimal places of more than 10 to the power minus 6, sorry, 1 to the power minus 6, that is 0. So I have multiplied 3 matrices, CS into RSABC into CS inverse. What is the output? Here is the output, RSDQ. Here you can see the output. This is the output. Okay, this is the output. Next is RRDQ. Where is RRDQ? This is RRDQ. What is the value of RRDQ? CDQ0R into RR into CDQ0R inverse. Here it is. RRDQ is what? Here you can see sim dot simplify in bracket CR into RRABC into RRABC. Okay, into CR inverse. And I've simplified it. What is the output? RR00, 0RR0, 00RR. I'll just quickly write here on solving. We get what we get? RSDQ is equals to RS only, which is nothing but RS00, 0 small RS0, 00 RS. This is what we observed, right? From the code. Similarly, RRDQ. This was RRDQ, right? Yes, RRDQ, which is a 3 cross 3, is what? It is nothing but the original RR matrix in ABC. So there is no change in the resistance matrices. Correct? Okay. Next is what? ES matrix, ES in DQ. What is the ES in DQ? Here you can see sim dot simplify CS into differentiation of CS inverse. Correct? Here you can see CS into CS INV dot DIFF of T. So in MATLAB, in Python, how do you differentiate a matrix? You have to write dot DIFF of T. DIFF of T means differentiation with respect to time. So here it is nothing but multiplication of two matrices, CS into d by dt of CS inverse. So what is the output? 0 minus omega 0, omega 0, 0, 0, 0, omega. Now why it is omega, why it is not in terms of sigma is because I have mentioned the values of sigma as per the convention. So if the convention is 3, so as per it, it has taken the value of sigma. Otherwise, I can write this equation in terms of sigma and psi only. So here, what I got is ES in DQ, which is nothing but a 3 cross 3, is what? Sigma into omega 0, 0. Sorry. It is 0, sigma into omega 0, minus sigma into omega 0, 0, 0, 0, 0. Here, as sigma equals to, what was the sigma? As per third convention, what was the sigma? Convention 3, sigma was -1. As sigma equals to -1, third convention. Okay, so this is what we got. Is what? 0 minus omega 0, omega 0 0 0 0 omega. Correct? We were here. Correct? Here also we got the same thing. Just it has substituted the value of sigma. What is ER? ER is differentiation of multiplication of CR into CR inverse. Sorry, CR into d by dt of CR inverse. And what is the value of it? You can see here. I'll write here ER in dq 3 cross 3 is what? 0 sigma into omega minus omega r 0 minus sigma of omega minus omega r 0 0 0 0 0. Okay, so you substitute the value of sigma, you will get the answer. Okay, so we have found all the matrices of the voltage terms, voltage equation. Now we want to find the matrices of the flux equation. What are the four matrices? LSS dq, LRS dq, LSR dq, and LRR dq. We have to find it. Okay, so we'll find what is LSS in dq, which is nothing but 3 cross 3. What is this? We'll find. What did the code give us? This is the value. LSS dq is what? What was the LSS dq? Sim dot simplify CS into LSS ABC into CS inverse, right? Multiplication of three matrices. And after simplifying, what is the output? This is the output. LLS plus 3 by 2 LMS 0 0 0. LLS plus 3 by 2 LMS 0 0 0 LLS. Similarly, LRR dq you can write as LLR plus 3 by 2 LMR 0 0 0 LLR plus 3 by 2 LMR 0 0 0 LLR. Similarly, LRS dq equals to what? So LRR dq is fine. LRR dq is sim dot simplify of CR into LRR ABC into CR inverse. Similarly, what is LSR dq? LSR dq is CS into LSR ABC into CR inverse, which is nothing but C dq0s into LSR into C dq0R inverse. What is it? It is this. Both are equal. LSR and LRS both are equal to 3 by 2 MSR 0 0 0 3 by 2 MSR 0 0 0 0. Did you observe something, some advantage? None of the matrices are a function of theta r. So all the matrices are constants. Earlier, the inductances in LSR, LRR in ABC were a function of theta r. Here, none of them are function of theta r. Means all the matrices are constants. And you can easily find the parameters of the machine, which are based, if you do no load test on the machine, you can easily get the parameters of these terms: LSR, LMS, LMR, MSR, RS, RR. Omega R, omega R you can get from the rated, the nameplate parameter of the machines. And sigma is the speed, omega is the reference time in which the motor is modeled. So after finding this equation, you have to substitute. Omega is either omega S, either omega R, or 0. So basically all the three terms are known. So all the equations you find here, if you substitute the values of these matrices in the above equation, you will find all the dynamic equation are constant in nature. So one final equation in terms of dq you will find in this code only. Here I have written So first I have written VS in ABC, VR in ABC. IS means basically all 3 cross 1 matrices I have mentioned, voltages and voltages, currents, flux for stator and rotor in ABC and DQ. I have mentioned all of them, and I have finally written the two equation in terms of voltage, two equation in terms of flux. Means basically these are still ABC. If you write in terms of DQ, what you'll observe is Vs dq is Rs dq into Is dq plus d by dt of lambda ds plus Es into lambda ds q. What is this? Its value is this. Okay. Rs into Ids minus omega into lambda ds plus d by dt of lambda ds. In place of omega, you substitute either 3. Omega s, omega r, or 0 based on the choice of reference frame in which you want to model the motor. If you want to model the motor in the synchronous reference frame, in these equation, you substitute omega equals to omega s. If you want to model the motor in terms of the rotor reference frame, then you substitute omega equals to omega r. And if you want to model the motor in the stationary reference frame, you substitute omega equals to 0 in these equations. Then you will get the dynamic equation in that respective dq0 reference frame as per any convention. So in the above line, I have written a line where I mentioned the convention. CONV, that was the code. So here in this code, if you just replace CONV from 3 to 1, so there you can get the dynamic model of the equation in that convention, in that DQ reference frame. So these are the final dynamic equation. Okay. Here. VDS equals to RS into IDS minus omega of lambda QS plus d by dt of lambda ds. Similarly, these are the rotor equation. So what you observe is stator equation, there are some additional terms in terms of omega. So in the equation of VDS, you will find minus omega of lambda QS, means there is some cross coupling term. In the equation of VQS, you will find the term plus omega into lambda ds. So you will find a cross coupling term of ds in QS and QS in ds in the KVL equation. Similarly, for rotor voltage equation, you will find in the equation of VDR, you will find the cross coupling term of lambda QR, which is multiplied with omega minus omega r, minus of omega minus omega r. So there is some cross coupling term in the stator dq and the rotor dq equations from d axis flux to q axis flux and so on. Similarly, here you can see that the inductances are all constants. They do not depend on any angle. So that's why what you do is, for simplicity, you model the induction motor in DQ reference frame. In any DQ reference frame. That is your choice. Omega equals to omega s, omega r are 0. That is substitute. And you can choose any convention, 1, 2, 3, or 4. In general textbooks, in electrical engineering courseworks, generally the third convention is preferred. Why? Because the third convention, we have already seen that in the previous lectures, that the DQ phasor, the space phasor in DQ for the third convention is nothing but XD plus JXQ, which is very simple to represent. So that's why we generally take the practice of choosing the third convention. And when it comes to the choice of the speed of the DQ reference frame, you can choose any speed, omega s, omega r, or 0. Okay. Generally, for the closed loop control of induction motor, omega equals to omega s, means the synchronous DQ reference frame is selected with the third convention. Okay. So this was a Python code which will give you all the calculation, and you need not solve this whole mathematical analysis, this all matrix multiplication using pen and paper. You can even solve this in MATLAB by using the so in Python there is a library called sympy, symbolic math library. Similarly, you can use this respective the symbolic math library of the MATLAB and derive the equation of the induction machine in the DQ reference frame, in any arbitrary DQ reference frame. So here what you observe, that whatever is the DQ reference frame, let omega be omega s, omega r, or 0, the inductances are constants. Let the convention be 1, 2, 3, or 4. Still the inductances are constants. So that's why in induction motor, there's a flexibility that you can model the motor in any DQ reference frame with any speed of rotation and any convention. Why? Because of the symmetry. Stator also you can. Why? Because in induction motor, if you just see the equivalent vector representation here, you can see stator and rotor all has almost the same three-phase distributed winding representation. So basically, you will find that there is a symmetry between stator and rotor. There are distributed winding in stator, there are distributed short-circuited winding in the rotor. So there is a symmetry. Because of this symmetry, that's why you can model this induction motor in any DQ reference frame, rotating with any speed. But when it comes to other AC motors like a permanent magnet synchronous motor or only synchronous motor, the salient pole on cylindrical synchronous motor, there you can't model the motor in any random DQ reference frame. In that case, you have to model motor in the rotating DQ reference frame. Then only it is advantageous. But it's not the case in induction motor due to the symmetry. You can model the induction motor in any random, arbitrarily rotating DQ reference frame with any convention, because you will get constant matrices in for all the cases. So this was the today's topic of modeling the induction motor in arbitrary DQ reference frame by using the matrix transformation. Here we have just used the matrices, multiplied the matrices and got the equation. But there is one more way to get these equations, the same equation, but different approach. The approach is nothing but space phasor analysis. That for that approach we will see in the next lecture. In the next subsequent lecture, we'll see how to derive the model of a three-phase wound rotor induction motor in DQ in an arbitrary rotating DQ reference frame. But instead of using matrix, we'll use the space phasor concept. So here we observe that if you want to model the squirrel cage induction motor, what you do is put this 0, VDR is 0, VQR is 0, VOR is 0. Why? Because the rotor is short circuited. So the voltage is 0. 0 voltage is induced. So that's why to have a generic model of induction motor, we have considered the slip ring or the wound rotor induction motor for the study. Why? Because we want symmetry. We want 3 voltages, 3x1 matrix for voltage and 3x1 matrix for the rotor voltages. So that's why we consider a very generic term. So once we have a generic model of induction motor, here you can see that these matrices are only function of the constants and some other constant like sigma, which depend on the choice of reference frame. So we have done a very generic model of wound rotor induction motor in arbitrary DQ reference frame. And later, based on what is the choice of your omega, convention, and the type of the rotor type, that is squirrel cage induction motor or wound rotor induction motor or slip ring induction motor. Later you can substitute based on the choice of these 3 selections in the final equation. Then that will be modeling of the induction motor in that respective scenario. So I think that's it for the day.